algorithms and social networks. So just to clarify a little bit of notation or nomenclature, when I talk about a social network, I'm talking about individuals, and these could be humans or, if you want, animals or other social creatures, and their social interactions, and we think of these as nodes and edges. And some examples of the kind of networks that we'd be thinking about, what these social interactions could be. It could be friendships, relationships, collaborations, supervision, in which case we now get into directed domains, seeking advice or recommendations, or just physical proximity, which matters in many cases. Some of the classical functions, social networks help you spread information or recommendations. On the downside, they spread diseases or harmful rumors. They provide opportunities for trading, for collaborations, for joint actions. So people you know with, you're more likely to undertake certain tasks with. They also confer status within a society, depending on who you're connected to. And so this is sort of going to be a talk a little bit about some personal perspectives. Let me conjecture, why do we in this community, and I know not all of us work on this, but a large number of the people in the room, like social networks? Well, first of all, I would say lay people can very easily relate to the topic. If you're trying to explain what you're working on to someone who does not have a math or computer science background, you can always tell them about their friends and Facebook, and mention things like 6 degrees of separation and Kevin Bacon games, and it's all really beautiful, and you can easily have cocktail party conversations with people, which gets a little harder when you work on trying to prove equivalences between quantum complexity classes, for instance. Many of these interactions that I just described are pairwise by nature, so they're easily modeled with edges, and this means we have graphs, and in our community we just love graphs with a capital L. So anything that we can model as graphs and that leads to new algorithmic questions on graphs is very welcome here. These networks are formed and used. They constitute individuals that have their own goals, their own motivations. And over the last few years, our community has gotten very excited about game theory and economics. So a lot of these wonderful new toys that we have just acquired can be nicely applied here. And similarly, these things are large scale. Humans behave very unpredictably in many ways, and we can nicely model this with randomness. So all the beautiful work that we've been doing on analyzing random processes, again, can be applied quite nicely. And different communities thinking about these topics have different weights on these parameters. So this is the view that physicists really like. Economists like this view a lot, obviously, but I mean, all of them are really some kind of a combination thereof. Let me sort of mention a few other things that we like besides graphs. We like our models to be very clean and simple, and we like to optimize things such as objective functions. We also like to model individuals as optimizing things. And I think that's sort of starting maybe to get us into trouble occasionally. Humans are not always clean and simple. They don't always optimize something that we can express that nicely as a numerical objective function. And often if we try to encode the quality of what we find in just one number, as we like to do, I think we might get ourselves into trouble a little bit. We love to modify and generalize and vary our models. So once we have found one clean basic model, we love attaching all kinds of bells and whistles to it. I would like to posit that we should be a little careful with that if the model that we are departing from was already unrealistic to begin with. And sort of we came up just because we like simple models, and now we attach bells and whistles. It's not really clear how fruitful of a direction that might be. We love tight and matching bounds. Whenever there is a log n gap between our upper bounds and our lower bounds, that is a personal insult and a challenge that needs to be overcome. So I would say that, again, depending on how realistic our models are and how meaningful the question is and how close of an approximation our objective function is to what we're really trying to do, it's not completely clear that always matching these bounds perfectly is sort of the best way to spend our time. And finally, we love structural insights. Sort of understanding structure. So raise your hand if you have ever written a phrase in your papers like, lemma 4 might be of independent interest because it reveals structural insights into the nature of networks. Keep your hand up if you have believed the sentence every time that you've written it. It's sort of our nice cop-out, right? We prove some nice structural theorem about something, and it's really beautiful, graph theoretically speaking, but somehow whether it really tells us something about the processes that are underlying it, whether it really tells us about human nature or the structure, in some cases it does, but I think we might have to be a little more careful. A lot of it is contingent on the models. And so what am I going to talk about in this talk? Sort of just sharing some personal thoughts on the work that's going on in our community, and specifically, so I would say this sort of branches into two directions. One is algorithms for actually dealing with social networks as an input, and I'll give you a few examples. And the other one is the algorithmic view of what the social network itself does in terms of computation. I want to give a big yellow warning caveat sign here. I'm not speaking on this with any kind of authority, except that for some reason the organizers in their infinite wisdom chose to bully me into giving this talk. So these are a lot of personal thoughts, and if you disagree with them, and if I seem to be speaking negatively about the work that you love the most, I hope that's the start of a discussion rather than the start of a never-ending feud between us. Also, those of you who were yesterday in the breakout group on social networks might find that there's a bit of overlap, and I mean, obviously some of us in the room at the time had similar concerns. So let me talk maybe first about, very briefly, I'm going to talk very briefly about three topics. And first one is one that I've worked on a little bit in the past. So this notion of spreading influence in a network, or if you want to take a more monetizing view, viral marketing. The goal is to find a small node set that somehow has large influence in the network, and influence is usually defined in terms of you look at some natural activation model, some natural way in which by an epidemic process, information or something like that spreads through the network. And if you have a set that together somehow reaches a large set, maybe under probabilistic model, then you say this might be an influential set. The general operational view is here we have a few nodes that start active, by which we mean they bought the product, they have this piece of information, whatever it is we're analyzing. These active nodes may cause others to activate, and there's sort of two natural classes of models that I think the community has looked at recently. One is for each node pair you have some kind of an independent probabilistic attempt at activation. These sort of have been called cascade models. Or you have node-based thresholds, and nodes become active when some number or weighted number of active neighbors exceed this threshold. So just to illustrate this briefly, so you have this small network here, and you have these blue thresholds, and you start with the node active, and that makes other nodes reevaluate what percentage of their neighbors are active, and that might cause future activations. And after a while, you sort of stop and it peters out, and this would be the influence of this node, and then you take the expectation of this over the random process. So this leads to a number of interesting questions. In particular, we could now do one of the things we love doing, and that's optimizing influence. And so this was some past joint work that I did with John Kleinberg and Eva Tardosh. So we could say our objective function is, let's say, the expected number of active or infected nodes or reached nodes if we start with the set S. And so we could say, what can we say about maximizing this set under some constraints? And turns out that maximizing this is hard, and it's hard to approximate with certain factors, and this depends on the precise model, whether we're assuming the thresholds are random or they're given. Approximating is much harder with given thresholds than with random thresholds. On the other hand, if the thresholds are uniformly random, or if we look at this independent activation model, the cascade model, this function f is monotone and submodular, which means that you get a 1 minus 1 over e approximation out of greedy algorithms. And it's kind of nice. So if you can do something, you can find the approximately most influential sets of nodes. There's a beautiful generalization of this original result of ours by Moselle and Roch in 2007, which showed that you don't have to just add up or take the number of neighbors or a weighted number. You can take any locally submodular function that determines how likely you are to be activated. And if you have uniform thresholds, then you still get overall the monotonicity and submodularity, and therefore the approximation result carries over directly. So, in our original paper, and I think in many subsequent papers, these random thresholds have been modeled as, or have been justified as modeling lack of knowledge. So we don't know how likely this, or where this person's threshold is, so let's just assume they're uniformly random. But so that raises a slightly troubling question. How realistic is this? And does this mean that all of a sudden, if we had a lot better data, if we had done some market research to figure out what is an individual's propensity to reacting to peer pressure, all of a sudden exploiting this extra knowledge makes the problem so much harder to approximate, because it goes from constant factor hard all the way up to polynomially hard to approximate. So that's a little bit troubling, and in a sense, I would say that it also might be, sort of in particular in the light of subsequent work, a little bit of our tendency to sort of fit the model and the question we're asking to the tools we have available. That we know that we can run greedy algorithms if we have a submodular function. If it takes making the thresholds random in order to be able to optimize this, then let's do that. Yeah, David?
Is it important to be uniformly random, or is
yes.
it prior such as?
Uniform random. I mean, if you make them sufficiently sharply concentrated, you can get them into the range where you have these sharply changing behaviors, where you go from nothing to everything to nothing. So, since our paper, there's been quite a few extensions here. So people have extended the models to take negative recommendations into account when you have cascades of one person recommending the product and someone saying it's crap. You have negative friendships, where some of your friends, if they recommend a movie, you know, okay, that's the one I'm not going to see. So you can put that into the model. There's quite a few other modifications, and then you can take a few steps that sort of go beyond this basic model and say you can now do pricing of products, you can do discriminative pricing, and you want to maximize profit and so forth. So there are many ways in which you can sort of push these models further and turn this into maybe a more realistic problem in terms of marketing. So the approach in many of these papers is by careful choice of models, or maybe in some cases also naturally, what happens is the objective function that you're trying to optimize ends up being submodular, or in some cases monotone and submodular, and then you can apply known techniques. So optimizing a non-monotone submodular function, we can approximate it within worse factors, but we can approximate it. So this is very nice. But so one question we might want to ask ourselves here is, are models driving the algorithms, or are the algorithms driving the models? Are we carefully modeling the problem in such a way that we can use an algorithmic technique that we have already worked on for the past few years and that we've come to know and love? Or are we really choosing our models in this way because we believe that this is the way the world really works? And I don't have the answer. I'm really just posing the question, but we might have to be a little careful there as a community. So the other issue there is that these models have incredible numbers of parameters. You have the strength of the link, you have the functions locally at the nodes. Where are we going to get these data from? And of course you could say, well, if people reacted the same way, if the network acted the same way on each of them, this would be nice, we could use some inference. And there's been some beautiful recent paper by Andreas Krause and Jura Leskovec and some people on doing some inference. I think Jim Aspen has had a paper on this a couple of years ago. But that would be assuming that you follow the recommendations of your friends the same across products, and there may be a lot of variation here. So these are beautiful models, but I'm not sure how far we're ever going to go push those into the field if we're really thinking about algorithms in the field here. So let me move to another topic that is very popular in a number of communities, namely communities. So communities in network are informally defined as sets of nodes that are unusually densely linked to each other. And so here I've shown you a graph, and I've shown you a bunch of edges, and we could ask ourselves, well, what are the communities in this graph? And there are different formulations, obviously, of what we want to do. We might want to find one community, maybe one at a time. We might want to find multiple overlapping ones, or maybe we want to partition the graph into disjoint communities. Maybe once we have found them, we want to actually interpret them. What do they stand for? What is the meaning of these communities? And obviously in this picture, I mean, this would be one natural interpretation. You have 3 communities here. Or you might say, well, actually, really, we only have 2 of them. And depending on how you define it, you could come up with one or the other answer, and we could argue about which one is right here. So long as we don't know the semantics here, it would be a pretty pointless argument. So there are many ways to formalize the notion of a community, depending on where you come from. So here, among theoretical computer scientists or algorithms people, we love sparse cuts and conductance and similar approaches. So we've looked at communities in this sense. Physicists have sort of become really enamored with this notion of modularity that was proposed by Girvan and Newman. It's very similar to correlation clustering objectives in our community. And as far as I know right now, there are no provable approximation guarantees for this objective in general. So if you do like the kind of technical questions, you might want to look up some of those hundreds of papers that the physicists have written on it, which are mostly heuristic-based, or almost exclusively heuristic-based. Would be an interesting question to bring some of our techniques in. Obviously, spectral interpretations, like what can we do if we look at eigenvectors and eigenvalues, dense subgraphs, dense as k subgraphs. Can look at it from a probabilistic model and try to infer things in Bayesian models, chains of overlapping clicks, and if you go into enough conference papers, you will find oodles and oodles of other models here. So in our community, we love graph cut objectives. Physicists love their optimization heuristics. So again, part of it is, well, how are we trading off here insights versus the techniques we love? So why do we believe that one objective is the right one? And we might want to evaluate that a little more rather than propose a model based on the techniques that we have readily available. So let me share with you maybe some directions that I think are perhaps a little understudied and that I think would be worthwhile to pursue, just personal opinion. So maybe returning to the question, are we trying to optimize objectives, or are we trying to actually find out something interesting, some truth about the network? And I think one very beautiful paper that did something similar in terms of clustering in a metric recently is by Nina Balkan, Avrim Blum, and Anupam Gupta, 2009. If I may paraphrase it in this context a little bit, is suppose that you have an NP-hard optimization objective here, and you're going to run an approximation algorithm, and it's going to give you pretty good approximations. But what you're really looking for is some ground truth clustering that corresponds to your individuals. So if you believe that your approximate solution is good enough and will give you something that's close to ground truth, because otherwise why are you bothering if you're trying to find ground truth? You're using optimization as a proxy in the first place. So if you believe this is a good proxy, what does that tell you about the assumptions about your model? Does that mean that your graph already has a bunch of nice structure? And if it does, then maybe you didn't even need all your high-powered machinery. And sort of from the physics side, Good de Montjoie and Aaron Clauset sort of looked at this sort of from a little bit more heuristic and example-based perspective, but I think they arrived at a very similar point to make, that if you're using some objective function as a proxy for finding ground truth, you might ask yourself the question, what does it mean if this objective actually captures what I'm looking for? So I think that's a question that in this context hasn't been studied nearly enough, and I think it could use a little more studying. Another direction that's completely orthogonal here, but that I also think we might want to look at a little more is what happens with graphs evolving over time, and in particular the notion of communities. So when we look at a community, it's nice to sort of say, oh, look, I found a community, and I almost found exactly the theoretical physicists, except for these 5 or 6 people that somehow I included wrongly, and these 3 people I left out. Okay, and now what? I think what might be interesting is to track these things over time, and how does the nature of a community change over time. And at this point, what even the meaning of a community is, if it evolves over time, I think is a philosophical and a mathematical question, and certainly finding and visualizing them would be quite interesting. And again, I think maybe we want to go one step further. Rather than just running algorithms and producing sets of nodes, maybe we want to also try to understand them a little more. And this is deliberately or by necessity vague. What is the function of a community? Does this kind of algorithmic goal that we're pursuing really help us understand it? And finally, I want to come to the other side, algorithms that happen in networks, and want to briefly talk about small worlds, which I'm sure many of you have already heard about. But again, sort of wanted to share just a few cents about it. So at a sort of very 30-second summary level, small worlds are a graph model that is trying to explain the coexistence of both local clustering in graphs and small diameter. And the basic model was proposed by Watson Strogatz and then sort of modified by John Kleinberg in his paper from 2000 that has had a huge impact on our community. And the basic model is you have some local structure that induces a sort of nice metric. Think of it maybe as a two-dimensional grid or a d-dimensional grid for now. And then you have random long-range links. And think of the local structure as your friends that live close to you or that are work-wise close to you. And the long-range links are the people that you just randomly got into a conversation with on the plane and just kind of stayed in touch. And over there you have sort of a depiction where not everyone has a long-range link, but I just showed a few of them. And you could now choose different distributions for generating your long-range link, and you could ask some questions about what these graphs look like, what is their diameter, and so forth. And the theorem that I think really inspired the community in this context from John's paper back then was that if these long-range links have a probability distribution of r to the minus d, so the probability that your long-range link is at distance r decreases polynomially as r to the minus d, and d is the dimension, in our case here 2, then greedy local routing finds polylog length paths. So if I ask you to route from one place to another, and you just always forward to your long-range link if it's better than your short link, that this will find paths of length polylog n, and this is the unique exponent for which this works. So this was a really beautiful result because it explained not just the existence of short paths in social networks, which had been conjectured and then sort of to an extent experimentally verified by Stanley Milgram's famous experiment in '67, but it also explains why these humans who use basically some kind of a greedy routing strategy rather than having full BFS available to them were actually able to find reasonably short paths. So, very beautiful result. I think this one actually did give us some amount of insight, and it spurred, of course, a huge amount of follow-up work. Of course, one question that I think is useful to ask here is, does it actually match does this model match the data, or have we just proved a very interesting property of a very clean mathematical model? And so, with sort of knowledge from sociology that a large share of network data tend to be explained by geographical proximity, David Libnowell and a number of people, I think at the time at Almaden, but now distributed, did a large-scale study on live journal data to estimate this distribution. And they found that d equals 2 with a two-dimensional grid did not match the observed links at all. Okay, that's a bummer, but unfortunately they didn't stop there, and they said, well, it's no wonder because we don't really have a normal-looking 2D grid. Last I checked, the population density in Manhattan was higher than it is in Nebraska. So when you normalize for distribution, for density, you kind of need to change your distribution. And a very natural way to go about this is a rank-based model. So when you do that, you actually fit the data extremely well. So that's nice, and that, I think, motivated studying this rank-based small world model, and David Libnowell with Barbella and a handful of other people showed that a cautious version of greedy routing works under some technical conditions. So I think that's sort of a nice way to go about hand-in-hand, looking at the models that we have, extending them in directions, but having these extensions be actually motivated by some practical considerations. There have been a number of other extensions of trying to really pin down constants to do a little bit of breadth first search, and some of it seems like it's our, I don't know, knee-jerk reaction to trying to get upper bounds and lower bounds to match, if at all possible. I want to sort of maybe push a direction that I think has been maybe a little bit not studied quite enough. It's inferring this latent space. So, and this came up in the discussion in the social networks breakout yesterday, that in a sense, these social networks that we are analyzing, these graphs that we love so much, are really just a manifestation of something that's really underlying a latent social space. So these graphs, they're nice, but the friendships themselves don't mean so much as more they are indicators of something that is driving the formation of the friendship, that is justifying its existence. And I would say that for a lot of the applications that we've looked at here and also that other people have looked at, what we really care about is actually the latent space. It's not so much the friendships. So for instance, if you're talking about communities, you want to find the communities because they reveal similarities. And the edges are a proxy for people being similar. That's why we want dense subgraphs. So perhaps if we find the latent space first, we're really then doing the analysis in the right space. Similarly, if we want to talk about recommendations, want to do link prediction, if we have the latent space, I think we can go much further. And there has been some work on this recently. There have been 2 papers that used heuristics based on maximum likelihood estimation, one by Fregnault, Lebach, and Lotker, 2008, and then a recent paper by Lars Backstrom and Sun and Marlowe, in 2010, I think. And they had the nice property of not just actually proposing an algorithm, but running it on real data and seeing how much can you infer about where people are located from just a few positions of friends and all the friendship data. Now, as a theoretician, you sort of look at that and say that's nice and doing the MLE estimate, but that doesn't give you guarantees on distortions. It doesn't tell you how much you're over or underestimating how close individuals are in the worst case. Plus, I think this latent social space really isn't a metric. Dead. What we really do is we observe a union of metric spaces, and I think that is a direction we should go further. We have some paper under submission that shows that you can actually infer some of the latent social spaces. And so the take-home message is I think we should be a lot more careful with our models. When you look at economic models, if they predict something that's just completely wrong, if your model predicts that all social networks are stars, clicks, or empty, do not write another 10 papers about them, but start wondering whether you might have to change your models. Don't let our proxies obscure what we really want to do. Just because we have a nice objective or we have a nice structure, what is it that we really want to do with it? Let's not choose our model so we can apply what we know, but maybe go the other way. And sort of referencing David's talk from yesterday, sort of matching the toolbox, I think in our social network domain, one thing that we are doing differently from how David is applying his technique is we have our toolbox, but we're not handing the tools to the practitioners who come to them. We say, oh, this is a nice tool, let me now invent an application to apply this tool, sort of in the hopes that maybe it has something to do with reality. And I think that's sort of where we have to be a little more careful. And yeah, so maybe the most important upshot is we should learn a little more what the people who have been looking at this for centuries are actually doing.
It's about the middle point. So, this is saying that all models are wrong, but some of them are actually useful. From this perspective, it might be not a bad thing to actually choose those models for which we actually have tools to optimize, right? I think that Dan Locher was a big fan of this approach in computer vision, where many of the problems with information naturally are NP-hard, so you don't know really how well you can solve them, right? But if you reformulate them as polynomial time, you can actually solve them exactly. You can much better understand what's going on.
I certainly don't say that all the models we invent are wrong, but I would say there's a difference between inventing a really nice general tool, and that might actually have multiple applications, versus looking at a very specialized problem that you kind of invented to fit the techniques that you have. So if you have a very nice general thing that you can say, and you can say, oh, we study matroids because we can do things in polynomial time on matroids. I'm not saying we shouldn't do that, but if we're saying, well, we now specialize the problem and we put in these exact definitions, and then finally we've made our objective functions our modular, or we've achieved something, I think at that point we might not be saying much about the real world anymore. So I agree, it's a very fine line.
Last year in the vocabulary workshop, we have a little paper showing that with a slight modification of the modularity is exactly identical to the normalized type. It's very simple. Just one line proof. So
but
it's really a very,
but you have a slight modification, right?
yes, yeah, wow.
More questions? There's lots more. We'll continue. Oh,
Brian? Or
I don't really have a question. I just want to say thank you for making these points.
oh, you're most welcome. I put them on specifically for you.
Maybe I will input from a different field, an issue. Currently, with all the mobile phones, you are starting to have incredible amount of data. That might be something. So there is a community in computer science, in pervasive computing, communication, that is currently having a lot of interesting data about mobility of people, about interaction with people. So that might be maybe something that community with your community might be connecting in terms of looking at some of these graphs. I know that the social scientists are incredibly interested in this kind of measurements because they actually currently have social models that are on a very coarse level, right? Because of the surveys, they currently have maybe a day behavior and so on. These mobile phones currently are starting to provide minutes, seconds of interaction and communication measurements.